Basic definitions and terminology. And all, just from your experience in calc, that you probably know some of the stuff already, so bear with me, but you'll probably learn some new terms that you didn't know. All right, so differential equation is an equation containing derivatives or differentials of one or more dependent variables with respect to one or more independent variables. I feel like this screen is larger than the one we used to have. That's good.
Is anyone in that classroom?
Yeah. They just put us wherever there's space, unfortunately.
They have them here.
Yep. Okay. So, you've seen differential equations before. You're going to see a whole bunch of them that you haven't seen, obviously, in this course. One of the things that we need to be able to do is classify what kinds of differential equations we're looking at or solving. There's a few ways to do that, mainly three. One is by type. And we have two types, basically. We say an ordinary differential equation, which you'll hear referred to as an ODE. And, it's pretty much what it sounds like. It has ordinary derivatives with respect to a single independent variable. So, for example, dy dx equals minus x over y squared. This would be an example of an ordinary differential equation. Oh, sorry. Y double prime minus 2y plus 4. Y double prime minus 2y prime plus 4y equals 0, let's say. There's another example of an ordinary differential equation. This is implied that we have a dy dx, well, the second derivative, so d squared y over dx squared, y prime would be dy dx. So these are all ordinary differential equations. Second type is partial differential equations. And those look exactly what they sound like. Partial u, partial y equals minus partial v, partial x, partial squared u over partial x plus partial squared t over partial y equals 0. Yep, sorry. These are all partial differential equations. Pretty straightforward to classify them by type. By order, it can get a little tricky, but you just got to remember what it is that you're looking at. And that is the order of the highest derivative So for example, if we have d squared y over dx plus 3 dy dx to the fifth minus 4y equals x, there's only two derivatives. This first one is what order? And this middle one here is first order. So what would the degree be here? Or what order is this? Second order. Okay, so even though we have this fifth power here, we actually pay attention to the order of the derivative that has the exponent attached to it. Okay, so this would be a second order differential equation. Before we go on to the last type, just a little note here. A general nth order differential equation can be represented by a function, we'll call it capital F, of x, y, dy dx, d squared y over dx squared, and so on, all the way up through the nth derivative. So if you see anything that looks like that, I mean, that just means we have an nth order differential equation. Okay, and then we also have linear or nonlinear. Okay, linear is actually something we'll focus on quite a bit. The general formula for a linear differential equation is you have a coefficient possibly in terms of x. Sorry. You have a coefficient possibly in terms of x times the nth order derivative. And then we just decrease the order. So we'll use n minus 1 as a subscript of the coefficient. And so on and so forth. And then we have a coefficient of x maybe again, bless you, dy dx, plus a naught x times just regular y equals maybe a function of g of x. Okay, so the key here for a linear differential equation, if you look at all the derivatives, and the dependent variable. So the dependent variable in this scenario would be y, and then we'd have all the derivatives with respect to y up through the nth order derivative. We can say that y and all its derivatives are to what power? Sorry. So what exponent do you see attached to all these? That's the order. 1. Which is analogous to what you did in algebra, right? If the variable has an exponent of 1, we say it's linear. Just now it looks a little bit crazier. Okay? So this derivative is to the first, so is that one, and all the ones in between, and the dependent is also to the first power. Okay? The other condition for a linear differential equation is that each coefficient, so we're talking about the a sub k x's, depend on the independent variable, which in this case is x. Okay, if it doesn't meet these conditions, then we say it's nonlinear. Okay?
Has to be both of them?
Yes. And actually, we saw an example of that already, I believe. So if we go back to this one here, this one would not be a linear differential equation because we have a derivative that's to the fifth power. Okay, so that's what it would look like. Let's just try a couple of classification problems real quick. Let's say I have x to the fifth. Sorry. X to the fifth d cubed y over dx cubed plus 3x times dy dx plus 5y equals e to the x. Okay, so first, what order is this?
First.
Third order. Is this linear or nonlinear?
It's linear.
And the only other thing we have to classify this was whether it was an ordinary or partial differential equation. So which one is that?
Ordinary.
Okay. Pretty straightforward. Let's try another one.
Square.
Thanks.
Is it ever not squared or no?
No, it's always. Okay. So, what order is this? Second order,
Non-linear.
nonlinear,
Partial.
partial. Is there a question? We're good? Okay. All right. Any questions on classifying these?
First term wasn't squared, would it be linear?
Yes.
Wait, what?
If the first term wasn't squared, would this be a linear? And it would be. It should be a linear partial differential equation, second order. Okay.
And how come it like meets the coefficient rule thing?
Well, coefficients are 1, right? So constants could always be considered functions of any variable.
Because you can just like divide by x squared as well. So
Mm-hmm. So, we have 2 course goals. Whereas in calc we had like 84.
Should we write this down just like for our notes?
Yeah. I mean, these obviously there's little ones, but the main idea here is finding differential equations that model physical situations. So that's one of the big ones, is seeing a scenario and then being able to say, here's how the variables are related, so here's this differential equation that describes it. And then obviously finding solutions of these differential equations. That's the main idea. A lot of times we'll actually do things backwards. We'll focus on how to attack a certain kind of differential equation, and then we'll see, oh, well, here's all the applications that we can use these for. Okay, so we're going to see a lot of that kind of stuff. I could also tell you that we're not going to see any partial derivative or any partial differential equations. This is a introductory course in ordinary differential equations. Okay, so there's actually lots of different differential equations courses that you can take in college. There's this kind, there's partial diff EQ, there's more advanced coursework that you can do, but this is just an introductory course. Don't let that fool you, though. It doesn't mean it's really easy. Although some people would say that it's easier than Calc 3, so we'll see where you guys fall. Okay. Here's a definition for you. Any function f, well, I'm getting there.
Who's saying
It'll be within the little description here. Any function f defined on some interval I which, when substituted into a differential equation, reduces the equation to an identity, is a solution of the equation on that interval. I don't know why I keep switching from caps to lowercase. Just pretend you don't even notice. Maybe at this point you don't. Who knows? Okay. Pretty straightforward stuff here. So now that we know what solutions look like, which you already probably knew, and you probably know how to do this too, but we'll go through it anyway, you should be able to verify if you are given a differential equation and it says, here's a solution for it. You should be able to prove that it actually is the solution. So, for instance, let's say we have something like this. Verify that y equals 2x to the 1/2 minus x to the 1/2 ln x satisfies the differential equation 4x squared y double prime plus y equals 0. For all x greater than 0. Which is implied because we have that natural log function in there, but take 2 minutes. Roma, you can just think about it. Here's a solution in case you didn't get it to work out. But trust that you can get it. Just take the derivative once for y. From there, take it again, so you know what y double prime looks like. And then you just replace everything in the original equation with that, and it should all cancel out and give you 0, which is what's on the right-hand side. Okay. Hopefully you got all the derivatives right. Any questions? Roma, how'd you do?
Got it.
Okay.
Verified it.
Very good.
That's correct.
Okay. Any questions? All right. We should also say that not all differential equations have solutions. For instance, if we have y prime squared plus y squared equals -1, I think that's pretty clear that that's not solvable, right? You guys see why, yes? Right, because you have two squares, whether it's a derivative or not, you're never going to get a negative answer. Okay? What about y prime squared plus y squared equals 0?
Why is this equal to 0?
That's one answer. Y equals 0 works. We call elephant. We call this a trivial solution because you can look at it and say this is an answer. That's what we mean by trivial. There's more, obviously, but this is actually something that you can write down. Any solution that you can kind of just find by inspection, that's what we mean as a trivial solution. Okay? Let's see, what else? We also have...
Wait, but couldn't like a trivial solution for you not be a trivial solution for me? Like,
Well, if it is for me, and then I say just look at it, and then you're like, oh yeah, then we call it trivial.
Right, but like if you say that and I don't see it, I feel like, oh, this is easy, and then it's like some crazy thing. But,
It won't be.
alright. Right?
Explicit versus implicit solutions.
So do we not have to show work now? Can we just like write trivial?
Yeah, right. This is easy.
What do you mean, Mr. G? I knew the answer
Yeah.
was 0. I didn't
You don't see it?
go through all those
Just look
steps.
at it.
All right. Explicit means that the solution is in terms of one variable. So you'll have y equals some function of x. It is also possible to have an implicit solution, in which case, here's a little bit of Calc 3 coming in. You have a multivariable function equal to 0. Okay, so maybe it's very difficult to express y in terms of x, so we can just say, well, this whole function satisfies the differential equation. So this is an example of an implicit solution. In context, it might look something like this for now. Show that x squared plus y squared plus c equals 0 is an implicit solution for dy dx equals minus x over y. One way to prove that this is a solution for this equation is to take the equation, find out what dy dx is, and show that it works. Okay, so if we're going to find dy dx here, you'd have to do it how?
Solve for y. Plus it's different.
Or implicitly, but yeah. Implicit might be a little easier.
Look it up.
So if we're finding dy dx implicitly, first term would just be 2x plus 2y times dy dx. Derivative of a constant is 0. Derivative of 0 is certainly 0. And if you isolate dy dx, you get minus 2x over 2y, which is exactly the same as minus x over y. Okay, so this verifies that this implicit function up here does satisfy the differential equation. Okay? Let's see. We don't have to do that example. Let's just finish with a few remarks. And then we'll call it a day. Okay, so here are some remarks. Things that you'll see or get to know, but that you will have to know by the end of the course. The number of solutions for a differential equation is typically infinite. Here's an example of one. And I mean, this is easy to see that if we have a parameter c in the equation, that c can be really anything we want it to be, but it still satisfies the differential equation. Okay? Solving a first order differential equation. So we're talking about f of x, y, y prime equal to 0 usually yields a family of curves g of x, y, c equal to 0 as a solution. Now, if you solve an nth order differential equation, so now we're talking about f of x, y, y double prime, y triple prime, and so on, all the way up to the nth derivative, you would expect a family g of x, y, and now here's actually, this is a very important connection, and you'll see that as we actually solve. A first order differential equation has one parameter or one constant as part of the family of curves. An nth order differential equation is going to produce not just one, but n constants. So we'll say C1, C2, and so on.
Can't you just add them all together and get C?
Well, not necessarily, because they could be coefficients of functions. You couldn't just say, you know what I mean? For example, you could have a solution that looks like C1 e to the x plus C2 sine x. You couldn't just say, well, just add the constants together to get a new one.
But can't you get like coefficients for the second one too?
What do you mean?
For the first order, they're following differential equations. Like, you're going to have coefficients there too. Why not? Stay close.
Well, we have one coefficient, or one solution, with one parameter here. I think it'll make more sense when you start seeing these in context. Okay. This is an n parameter family, so you need to know that. First order gives you a one parameter family of solutions. nth order produces an n-parameter family of solutions. A solution, yep, free of arbitrary parameters. Hi. No, she is in California.
Cool.
That's why I wasn't there either.
Oh, no. Are you gonna have, you're gonna have her again?
Yeah.
Such a fun for a free sandwich for Ryan. I expect her to get it, not you to use it.
I don't know if I can promise that.
Or don't order one that you have it and give her half.
Yeah. Here's your free sandwich.
Sorry,
No problem.
man.
A solution free of arbitrary parameters is called an arbitrary, or no, I'm sorry, a particular solution. So, for example, if we have y equals c e to the x, and then for c equals 1, we have y equals just e to the x, this is a particular solution of whatever differential equation that is. What do you mean? Oh, 0. Yep. There we have that. One last one. I should just keep going since so many of you packed up right away. Drives me nuts. Sometimes the differential equation has a solution that can't be obtained by specializing the parameters in a family of solutions. We call that a singular solution. So we need to know what a particular solution is, a singular solution is. You should know about the different parameters that arise when solving different order differential equations, and that's pretty much it. The first section is done. The homework has been posted.